Yeah, okay, so we have this cute little USB spectrometer. So this is a visible spectrometer. It's essentially the light comes in here. You know, we had our Cheez-It spectrometer last time with the little slit. The light goes through the corner of the Cheez-It spectrometer. Here it comes into this little port. There's a fiber optic cable here. It hits the diffraction grating, which is that little plastic piece that you were looking through, and then it is the little rainbow is sent over to the detector. So it's got a little camera element in there, and that was your eyeball. So it has all the same parts as our spectrometer that we used last time, and we can see the light. Here's a tungsten light source. It's kind of hot, but it's a bright white light, and it's giving a continuum spectrum. So that's just a vocabulary word that I think you should put in your mind, and that is when all of the wavelengths of light are in the spectrum, it's a continuum. Okay, compare that to what we saw in the Cheez-It spectrometer when we looked at the mercury lines. See, there's the mercury spectrum. And so when you look through the spectrometer, you saw those individual lines, the rainbow lines that you saw, and that was a line spectrum. So we talked about spectral lines in class last time. These are the spectral lines of mercury, okay? And then when we're looking at just a hot, solid object, we get a continuum spectrum. Now, if we put this on something red, so here's the visible spectrum from 400 right here, 400 wave number or nanometers to 700 nanometers. This is blue over here. This is red over here. So if we put it on red, the red light should still be reflected back into the detector. The blue light should go away. So let's see if that works. So we're going to stick this thing right on the red. See, the red's gone. Let's put it on the blue. So the blue, this side should not be changed. That side should go away. So here's the blue. So there's a little bit of red, but the blue is really gone. Here's green. Blue, green, red. Okay. Here's yellow. Yellow and red look pretty similar, but it's got a little bit of green in it. There's white, there's the red. So your eye, the pigments in your eye are being tickled by these different wavelengths of light, and they interpret the colors. So when you see this, you're seeing that spectrum on your eyeball, on your retina, and your brain is matching it to what you call. We call it red, green, blue, yellow, and so on. We have to learn those names, but your eye is doing the spectroscopy. So that's red, that's green, and that's blue. And you could mix those three colors and get all the other colors of light to tickle your retina the right way. So anyway, that's a little bit of spectroscopy. It's kind of fun. Since I had the system set up, I thought you guys might like that. If you like that, then take PChem. I'll see you then. So. But we got a lot to do today, so let's get busy. So last time we learned all about light and the equations related to light. We talked about line spectra of atoms and so on. And so today we're going to explain the theory behind that by looking at the different atomic orbitals. So what are the electrons doing in emitting light? And this is, I love this one, this me here. Because we talk about the SPD orbitals in our Gen Chem class, but we ignore the Fs. And there are G, H, I, and J, and so on orbitals, and we don't ever talk about those. Even in PChem, we kind of ignore those. And so we talked about it a little bit. And then, so we'll jump into this. So I looked at the Alex reports. There really wasn't much to show. There's like there was a handful of people that have already started the Wednesday one, so good job on that. We got a lot to do between now and Wednesday. So I covered all of the Monday Alex problems on Friday so that you guys could work over the weekend. So if you weren't here on Friday, go look at that video. And today we're going to start on the Wednesday homework. So we have Monday and Wednesday to cover all of this. We'll see how far we can get today. Okay. So this spectroscopy that we learned about last time, let's see, has allowed us to understand what's going on in the elements. Okay, so we get these elements in the gaseous phase, like mercury. So we have gaseous mercury in that tube light, and then we can see the line spectra, the things that the electrons are doing, and we can understand there's core electrons and valence electrons. What we're really seeing with the visible light in mercury and other atoms is we're seeing the valence electrons jump around. The visible spectrum is not really enough energy to analyze the core electrons. So this, again, as a result from spectroscopy, we know there's a difference between the core electrons and the valence electrons. So those are two really important vocabulary words that you need to have. So that's the idea of valence electrons. It's the outermost electrons. And if you look at the periodic table, here on this one, it's Roman numerals. So Roman numeral 1, 2, 3, 4, 5, 6, 7, 8 over on the right. So the S block and the P block, those are the valence electrons. And in ALEX and other periodic tables, it's up there at the top, it's the A's. So 1A, 2A, and then you jump over the transition metals and you get to 3A and 4A and so on. Those are the number of valence electrons. Those are the outermost electrons. And those are the ones that are going to do the chemistry, because those are the first ones that another element sees. And so this is one of the problems in ALEX, is to identify the valence electrons. So let's just do this. This is really simple. This shouldn't take you any time in ALEX. It says how many valence electrons are in these neutral atoms. And so there's two types of problems in ALEX. You've got neutral atoms and then ions, cations, anions, and so on. So arsenic, we come over here, we find arsenic in the periodic table, right there, and it's in group 5A. So you would just write in 5 valence electrons. Sodium, this should be super easy, up here 1A. So 1 valence electron. Boron, right here, 3 valence electrons. Iodine, we go find iodine. It's easier to find iodine than it is to find my pen. I can't ever find it. Oh, it's over here. Okay, iodine. Up here, 7. So 7. So anything that's in the noble gas, in the halogen group, iodine, here's chlorine. I don't even need to look. I know chlorine and iodine are in the same column. So that's 7. Tellurium, I go over there, it's in the oxygen group. So I come up from oxygen, that's 6. Phosphorus is in the nitrogen group. So it's 5. Nitrogen's also 5. See, they're in the same column. So if they have the same valence electrons, they should have similar chemistry. That's the reason we want to know about the valence electrons. Barium, 2. It's down here in group 2A. And then xenon. Even though they don't have a lot of chemistry that's interesting, the noble gases, they don't have a lot of chemistry because they have 8 valence electrons, and that's filled the P shell. So that would be 8. So those are pretty easy. We're not going to deal with the valence electrons on the D block. Okay, we have a course for that. It's advanced inorganic chemistry. So when you go into inorganic, then you're going to start looking at the valence electrons on the D elements. The F elements, we ignore it, just like that meme. That is a real meme. We do not really get into the actinide chemistry. That's like a very specialized part of chemistry. It's a very important part of chemistry. As we make nuclear fuel, we deal with the actinides. There are certain properties that the actinides have that are interesting, but it's just not, it's not a major topic in our curriculum. Okay, now ions. So how many valence electrons are in these ions? So we start, this first one's bromine. We're here, but it's bromide. So we move to the right one. Br minus has 8. And sodium plus. Okay, so here we're sodium. It's a cation, so we've moved left 1. Na plus. And notice this is element number 11. So a neutral has 11 valence, 11 total electrons, and if it loses one, it becomes like neon. So it's isoelectronic with neon. So Na plus is isoelectronic with neon. So it also has 8A. So this would be 8. Magnesium is element number 12. If I take away 2 electrons, then it would be like neon. But if I just take away 1, it would be like sodium. And so it would be in group 1A. So there'd be 1 for magnesium plus 1. Magnesium likes to be plus 2, so it would be like neon. Iodide, so I minus. Here, I minus. So if I put 54 electrons on iodide, then it would be like a noble gas. And so that would be 8. Cl plus, it's not very common, but you could strip an electron off of chlorine, and it would be like sulfur. So if I take an electron away from chlorine, it would be 16, and that would be 6 valence electrons. Krypton. I mean, you can ionize a noble gas, and if you do, you get krypton plus, it would be 7 valence electrons. So krypton has 8. If I lose 1, it would have 7. P3 minus. So here's phosphorus, 15. If I add 3 to that, I would be at 18. So I'd have 18 electrons, and that would be 8 valence electrons. N2 plus. So here's nitrogen at 7. If I take away 2 electrons, I would have 5 electrons. It would be 3 valence electrons. And then barium plus 1. If I'm at 56 for barium and I take away an electron, I'm at 55, which would be 1 valence electron. So these ought to be easy, right? We're just dealing with the 1A through 8A. We're skipping the transition metals. So you just use your periodic table, and you get one of those on the test. So hey, that's great. Not a problem. Okay, now let's sort of count valence and total electrons and so on. So there's some of these, and this is talking also about the shells, the number of electron shells. So we got magnesium. Here's magnesium. It's element number 12. So that means it has 12 protons. And if it's neutral, you don't see a charge up here. It's not magnesium 2 plus or anything like that. Then it's also got 12 electrons. So it has only 2 valence electrons. And so then it would have 10 core electrons. That's not one of the columns that Alex is asking about, but it's got 2 valence electrons, so therefore it has 10 core electrons. And then how many electron shells does it have? The shells, we'll find out, are the principal quantum number, and these are the shells down here. So magnesium is in shell 3, but in the core electrons, it has electrons in the second shell and the first shell. So it would have three electron shells. That includes the one that has the valence electrons. So this is generally a vocabulary quiz is what this is. Let's go to boron. Boron has 5 protons and 5 electrons in neutral boron. So here it is in group 3A. So it has 3 valence electrons. And it's on the second row of the periodic table. So it only has 2 electron shells. Now let's do argon. Here we are over on 18. It's got 18 protons, 18 electrons. That's 28. Okay. And there's 8 valence electrons. That means there's 10 core electrons. And then it's in the third row, so there's 3 electron shells. So there you go. Pretty easy. What is there anything that's confusing you about the vocabulary words? I'm going to go ahead just for grins and write on here a column right here that's core electrons right here, just because I want to see that, even though Alex doesn't ask you. So this is 10 of those. There's 2 core electrons for that, and there's 10 here. Notice the 2 core electrons is the fully filled 1 shell. Yes?
Will there be, from the last slide, transition metal?
There shouldn't be. Yeah, on the previous slide here. Yeah, because now, okay, maybe if they gave you like a vanadium, like let's take vanadium and subtract 3 electrons. So V3 V3 plus. Okay, you could answer that because V3 plus would be the same as calcium. And so V3 plus would have 2 valence electrons. So that might be the only trick I could think of. But what you're trying to do is you're trying to see in that group 1A through 8A, or the Roman numerals here in class, which of those there are. Okay, so now let's talk about these shells. So as we add the shells of electrons, naturally they're going to get further from the nucleus. So let's get our minds around the sizes of atoms. My kids had to deal with this because, yes.
Can you pass around the...
Yeah, there you go. Yes.
I was like, there's no way they're not made it to me yet.
That's right. That's right. Your little internal clock is going. That's fantastic. Okay, so my kids had to deal with this all the time, having a chemistry professor as a dad, right? We're walking into Target, and I see that big ball, and I was like, that looks like a proton to me, this big red ball. And I said, how big would that hydrogen atom be if that ball in front of Target was a proton? Because that's all there is in a hydrogen atom, a proton and an electron floating around somewhere. Okay, and so if this were a proton, which I estimated to just be 1 meter, a ball that's 1 meter, it's probably not quite a meter, but if that's a 1 meter ball, how big is the hydrogen atom? Okay, this is how big it would be. 74-mile diameter. Isn't that crazy? That's how dense that nucleus is. That contains all of the mass of the hydrogen atom. The electron is 1,000th of that. So when you look up here at hydrogen as 1 atomic unit or whatever, 1 gram per mole, that's really all the nucleus. That little 0.007, the electron is 0.001 of that. So the mass of the element is in the nucleus. Okay, and when we say that matter is mostly empty space, that's what we're talking about. The nuclei have all the mass, and the outer electrons are just doing all the chemistry. Okay, so that's how big a hydrogen atom is, and this is the radial distribution of the electron from the nucleus. So over here, this is the nucleus at 0 distance from the nucleus. We can plot this wave function for the electron, and this is the thing that we discovered with quantum mechanics, was that the thing that keeps the electron out of the nucleus is that it's behaving like a wave, not as a particle orbiting. Okay, so if you have this mental picture, it dates back to Niels Bohr of the solar system model of the atom. It's really not accurate. Okay, we don't have a discrete electron orbiting a positive charge. Okay, we have an electron cloud that is vibrating and staying out of the nucleus because it's behaving like a wave. Okay, and these are the waves that we have for that electron, and this is just the distance wave from the nucleus out to infinity. And so we have these different shells. So with the first shell, the n equals 1 shell is this red one, and you see the electron spends a lot of time close to the nucleus, but not in the nucleus, but it's close. The 2s, the second shell, notice the peaks hit their maximum further out. And then the 3 shell, the peaks are even further out. So as we add more electrons to the cloud, they naturally don't get close to the nucleus because this is already close to the nucleus, and electrons repel each other. So we got a 1s electron that's kind of surrounding the nucleus, and then the next electrons don't get sucked in very close. They have to stay further back because they're repelled by that 1s electron. So if this 1 meter target ball was the proton, and that was 74 miles, where's that electron on sodium, that valence electron on sodium? It has about a 3 meter ball of a nucleus, and that electron, the most probable position from the nucleus, is 971 mile diameter. Okay, so if this is the hydrogen atom, this is the sodium atom. So that's a huge difference in chemistry between sodium and hydrogen because of the size of the atom. So that's amazing. The sodium would be about the size of Texas, and hydrogen would be about the size of the 4 counties around Walker County. So 4 or 5 counties. So that's that's giving you an idea of how reactive the metals are or elements are as you get further down the periodic table. As you add more and more shells, it's easier for the elements to react. And that's what we call reactivity. So rubidium is way more reactive than potassium, and that's more reactive than sodium and all that. So it's easier to do chemistry the further the electron is from the nucleus. Also, that means that if you understand the valence electrons, which is our topic today, you understand the chemistry. Because as I'm coming close to Texas, I get to El Paso. If there's a sodium atom, let's say Carlsbad, if there's a sodium atom in Huntsville, I know it when I get to Carlsbad. So that valence electron is telling you what the chemistry is. If it's a hydrogen atom in sodium, I don't know until I get to Navasota. So chemistry is about that outer shell of electrons, which are called the valence electrons. Okay. So that's why it's so important. Now the radial nodes too, you see the waves oscillating? We have some places where they touch zero, and that's called a node. So the waves oscillate like this, and where they don't oscillate, this piece in the middle, that's a node. And this is just a picture to show that it's kind of expanding and contracting out of phase with itself, and there's a node there. So whenever we have waves, anybody play an instrument like a guitar or violin or something like that? You know about the harmonics, right? You have the fundamental, which is the whole string vibrating. If you touch the middle of that string lightly and pluck it, you get a harmonic, and it goes up an octave. Okay, and you can put numbers to that. Those numbers to the waves are quantum numbers because they jump in units. Yeah. So the harmonic numbers are what we're talking about when we talk about quantum numbers. So this is quantum mechanics. It's not as hard as you might think. Okay, just think about waves and the harmonic motions that you have of those waves. Every different type of harmonic you have has a different quantum number. Okay, so there's the principal quantum number that's really governing the distance from the nucleus in all directions. And so these start at 1 and go up to infinity. And so this is designating what shell it is in, and that's the numbers on the periodic table that go down. The period 1, 2, 3, 4, 5, 6, those are the principal quantum numbers for that shell. Okay. And then you have the angular momentum quantum numbers. This describes the shape of the orbital. So as you go around, think about planet Earth. It's a spherical system, roughly. And you have the principal quantum number, which governs your altitude. Okay, how far you are away from the center of the Earth. Okay, the angular momentum quantum number is like your longitude and latitude. So as you go around the Earth, if that were a wave, then there would be places where you would most likely be and places where you wouldn't be, and that quantum number describes your angular dependence. So that would be L starting at 0. Oh, yeah, there's another one going around. This is the one. Look for the one that's passed on. So the angular momentum quantum number starts at 0 and goes up to n-1. And this is a very important piece right here. So this list always stops at n-1. So if I have an n equals 4 shell, I can only go up to 3 with L. So 4 minus 1 is 3, so I can go from 0, 1, 2, and when I get to 3, I have to stop this list. And that determines what kind of orbitals I can have in terms of the angular momentum. And so we give those letters instead of numbers, because otherwise we'd have all numbers everywhere. So we call these letters, and we talk about s orbitals, p orbitals, d orbitals, f orbitals, and so on. And that's the angular momentum quantum number. We'll call it a quantum number, but we'll use a letter. We'll use the letter S or the letter P or the letter D. Okay. And then we have the magnetic quantum number, M sub L, and this is the magnetic field generated by that L. So you've got a distribution of the electron around the nucleus as it's oscillating, and it produces an electric or a magnetic field. And so this M sub L is the magnetic field component of that orbital. And this is also bound. So it's bound from minus L to positive L. So these are not ones right here. This is an L. So that's minus L, and this is positive L. So if I have L equals 3, then this goes from minus 3 to positive 3 with integers in between. So minus 3, minus 2, minus 1, 0, 1, 2, 3. So it's bound on both sides by L. And then we have the electron itself. So the electron itself, it's not, we call it spin, but it's not like a little ball that's spinning. It's behaving like a wave, but it does have a magnetic field as a particle would if it were spinning. So they called it spin because they didn't know any better. It's really behaving like a wave, but it has this tiny little magnetic field that you would get if you had a charge spinning on a wire. Okay. And it has a unit of 1/2, plus or minus 1/2. It can be spin up or spin down. And you can sort of mentally think of it as a spinning planet. And so if it's orbiting around, it can be spinning with its orbit, or it can be spinning against its orbit. So that's the plus 1/2 or minus 1/2 relative to the orbit it's in. So those are the 4 quantum numbers. Now, Wolfgang Pauli observed that no 2 electrons can have the same 4 quantum numbers. That's the Pauli exclusion principle. It's not in your notes, but we can put it in there later. But that's the requirement. And essentially, these 4 quantum numbers are like an address for every electron in the atom. So, we have carbon has 6 electrons. Every one of those electrons has a different address. Or serial number, if you want to think of it that way. And really, we can every electron in the universe has a different serial number because it's on a different atom, and once it's on an atom, then it has these 4 quantum numbers. So we can identify every electron in the universe using these 4 numbers, and if we could number every atom. Okay. So these are the shapes of the s, p, and d and f orbitals. So as we go around the sphere, the s orbital is just a ball. And these are the harmonic, these are called the spherical harmonic motions. So think about if you've ever blown a bubble. Next time you blow a bubble, you'll think of this. So you blow a bubble and it comes out, and maybe the whole bubble is oscillating like this. It's vibrating out and in all directions. That's what an s orbital is doing. So I've got an electron around a proton, and it's doing this. It's expanding in all directions and contracting like a balloon or a little bubble, and that's the s orbital, okay? What if you're blowing through your little wand and it forms the bubble, but it still feels the wind from your breath, and it starts doing this, where it's oscillating left and right, like that. If we were to map its changes, it's not changing up and down. It's not changing forward and back. It's only changing left and right. If we map that out, this is what the change would look like. So these are changes in the spherical shell. That's what these wave functions are supposed to indicate. Okay. It's not the shape of the electron cloud, it's a plot of the change of the electron cloud. So when we talk about the colors here, we might put a plus on the purple and a minus on the green. And all that means is that this little shell is expanding on one side and contracting on the other. And so this is the plus part, this is the minus part. But it's a spherical shell that's oscillating left and right. You'll see the oscillation. It's kind of a crummy drawing, but it's oscillating left and right like this. And if we plot the change, this is the shape that we get. So it's not an electron flowing around on that surface. You will see animated GIFs or GIFs, whatever camp you're in. Okay, you will see animations where it shows an electron going in a figure 8 motion, and that is trash. It is not true. Okay, so I wish I could scrub the internet over that misinformation, because that is not what's happening. Because if you think about that, how does the electron get from one side to the other by going through the nucleus? It doesn't. Okay, this is a bubble shell that's oscillating, and we're plotting the oscillation. So the plus and minus has nothing to do with charge. It's the deformation of the shell. Okay, So that's what's going on, and that's what's keeping it out of the nucleus. It's vibrating as a cloud. It's not passing through the nucleus to get to the other side. Okay, so I don't know why that's not taught more clearly, but in my class it is. Okay, so that's the L equals 1 shell. Now there's 3 directions: forwards, upwards, sideways, X, Y, and Z. So the P shell have, PX, PY, and PZ. So those are easy to know, X, Y, Z. And then the D shell. This is available for n equals 3, 4, and 5, and so on. This is L equals 2, and this goes from -2 to +2. And there's 5 of those. They're not easily designated X or Y, but they're like combinations of X, Y. So this might be like X times Y, and this might be X times Z, and this is Y times Z, and this might be X squared minus Y squared, and this is a Z squared combination. So we have combinations of X's, Y's, and Z's that we can assign to the D orbitals, and I'll teach you more about that in PChem. And then the F orbitals, this is L equals 3, and so there's 7 of them, right? Because it goes from -3 to +3. That gives you 6, and then the one in the middle is 0, so that gives you 7. So it's plus or minus 3, and then plus 0. So
your L is how many are away from the one?
L is what?
How many are on either side of the one in the middle?
Yes. Mm-hmm. Yeah, the one in the middle would be 0,
right,
and then the M sub L's. So it's 2L plus 1. You always get 2L because it's plus or minus of each of the L's, and then the plus 1 is the 0. So if I were to give you, and I wouldn't, but if I did, how many M sub L's are there for L equals 7? Okay, it'd be 14 is 2L plus 1, the 0. So it would be 15. So 2 times 7 plus 1. So anyway, that's what we've got. So these are the orbital shapes. Okay. And so let's look and sort of understand the directionality of these things. This is a problem in ALEX that would be really hard to understand if you weren't thinking about this oscillation and so on. So here's a sketch of this orbital. It's a p orbital, and it's saying that we need to compare the probability of finding an electron in this orbital. So if we're up here, let's say we're up here, we have a good probability of finding the electron because it's oscillating up and down like this. And that's one of the axioms or I guess one of the base assumptions or propositions of quantum mechanics is that where the orbital oscillates, that's where the electron's most likely to be found. Okay, we can't prove that, but that assumption matches the data. Okay, so if the assumption matches the data, it's probably a good assumption. Okay, but we started with that assumption in quantum mechanics, and it seemed to match the data, so we're going to go with it. Okay, but we don't really have a spoon small enough to get in there and scoop out an electron. Can't really tell where the electron is. We can only do that probabilistically, and that assumption that where the wave function is oscillating, that's where we're most likely to find an electron. Okay, so this is oscillating up and down, so that means we have a high probability of finding the electron along the z-axis, and no probability of finding the electron on the x or y-axis. So at point A, let's draw point A, 100 picometers behind the nucleus going along positive y. So I'm just going to put it down here on this positive y, so I have A back there. And point B is 100 picometers in front of the nucleus going along negative y. So I'm going to put it here. This is B. And in the ALEX, it's giving us 3 options: that the probability of finding the electron at point A is equal to the probability of finding it at B. It could be greater than, or it could be less than. Okay, look at A and B. There's no difference between A and B, so this would be equal to. So PA is equal to PB. That would be the answer that you would give. Okay, so then the next one, we'll erase those 2 points. Point A is 100 picometers to the right along positive x. So we'll put it right there. This is A. And then 100 picometers, point B is 100 picometers above along positive z. So here's point B. So the probability of finding an electron at point A is really low because the orbital's not going in that direction towards x, but it is going along z. And so probability of finding the electron at point B is greater than A. So we could, I think A is first, so we'll do point A. The probability of finding the electron at A is much less than the probability of finding the electron at point B. So it's just helping you understand how to interpret these orbital shapes. Where you see the shading, whether it's one color or another, that's where the electron's oscillating. And so that's where you're going to find it. Okay. And then this last one, we go to the left along minus x for point A. And 100 picometers below to negative z. That's B. And so here again, point A is going to be less than point B. I think that problem could be confusing if I didn't do it for you in class. So now you look at it, just draw your little points. What if we did one on positive and minus z, 100 picometers? They'd be the same because they're both along z. And so the only time you're going to get something different is when one's on a node, like along the x or y axis, and one's on the z axis for a p orbital. What if we had an s orbital? An s orbital, it's the same in all directions. So it would be equal, equal, equal. You know, if you were north and west or west and south, you know, it wouldn't matter. Now let's recognize orbital shapes. So we're given these four, it's kind of like a multiple choice, A, B, C, and D. Are any of these s orbitals? So let's just label some of these. I'll make it simple. This is what an s orbital looks like. It's a ball, okay? This is what a p orbital looks like. This is a p orbital. This is a p orbital. This is a d orbital. This actually is nothing, nothing, nothing. Those might be something, but we don't know them yet. Okay, so anyway, in this panel, are any of these s orbitals? The answer is no. Okay, and so if there aren't any s orbitals, you don't list anything, so you leave that blank on Alex. Are any of these p orbitals? Yes. Okay, if it's a p orbital listed, so we would put D here. Okay, so that's how you do this particular problem on Alex. Again, it's just getting you to recognize the shapes of orbitals. The shapes that look like this are typically bonding orbitals between two elements. And so like that might be the bonding orbital in a hydrogen molecule, but that's not an atomic orbital. So we wouldn't say anything about that. Here, on this second version of the same problem on Alex, are any of them s orbitals? Yes. Which one? D. Y'all see that? Okay, are any of them p orbitals? Yes. And then now we get to list A and C. So we put A and C. Okay. Questions on that one? Okay, good. All right, then we get into the energies of the subshells. So we talked about the quantum numbers, the N quantum number, the L quantum number, M sub L, and then the electron. We have all of them on this chart here. So if I have an electron right here in that energy level right there, and I drew a little up arrow, the up arrow means M sub S is equal to plus 1/2. Okay. Let's just go ahead, since this is a d orbital, let's just go ahead and write the M sub L's. So M sub L is equal to minus 2, minus 1, 0, 1, and 2. So you see every one of those orbitals has a different M sub L. And so this electron's address, it's in the M sub L equals minus 2. So it would be M sub L equals minus 2. So that's two of the numbers of its 4-number address. What is the L quantum number for this electron? Yes, how'd you know that?
Well, it has 2 with 0, and D's are always going to be equal to 2.
D is the one. So the L quantum number is that letter D. Okay, so the way I remember the L quantum number is what shape is an s orbital? It's a ball, okay, or a fist. Okay, how many fingers do I have up? 0. So the L for a s orbital is 0. Okay. And so, and you do them in order, S, P, D, F. So I think if I'm in a D orbital, I go S, P, D, L is 2. Okay. So I just count it out. S, P, D, L is 2. What about an F orbital? S, P, D, F, L is 3. What about a P orbital? S, P, L is 1. What about an S orbital? S, 0. No fingers are up. Okay. That's real simplistic, but you'll never make a mistake. You learn these little tools, and you got a D orbital, and you're like S, P, D. Okay, that's L equals 2. Okay, and then you'll always get those. So this is a D orbital, so therefore L is equal to 2. And then the 3 part right here, that is N. N equals 3. It's in the 3rd shell. So those are my 4. That's the serial number for that electron that I've drawn with the little up arrow. We draw the M sub s as up or down arrows. Okay. So these are the energies of subshells and multi-electron atoms, and they all have different energies. So you can see the 1s orbitals here, the 2s, and then the 2p, and the 3s, and the 3p, and so on. And this is a handy tool for learning the order of them. So if I'm building up an electron cloud using all the different electrons, I fill the 1s orbital first. So I could put like a 1 spin up and a spin down electron there. And then I could put a spin up and a spin down here in the 2s. And then for the 2p, you put them, each electron wants its own independent view of the nucleus. They're just like us. You don't want to be too close to people, right? If you got 6 chairs in the front row, okay, you probably want to space out, or let's take a theater, right? You put a chair between you and the next person, okay? That's kind of what electrons are doing. Yeah, there's a chair right here next to that first electron, but the second electron says, no, I'm good, I'm going to sit over here. And so they spread out first. That's called Hund's rule. They have the highest spin first, and that's the lowest energy configuration. And the reason that is because every electron has its own independent interaction with the nucleus. After we put 3 electrons in there, we're going to have to start doubling them up. So the theater's getting full, people have to sit next to each other. Okay, so then it's all full with 6 electrons in the P subshell. Where are we now? Well, we're 1s2, 2s2, 2p6, 6 electrons. How many electrons is that total? That's 10 electrons. We're at neon. So that's the neon cloud here, and everything's filled up. That's why neon is so stable. We put 1 more electron in. It's in the 3s orbital, out there by itself, 900 miles away from the nucleus. Okay, easy to steal. That's where sodium is. And so now we see why that's so easy to pull that electron out of sodium. If I get rid of it, then I've got this nice neon core here. So what we're doing is what's called the configuration, electron configuration of the electron cloud around the different elements. And we can understand the chemistry if we understand this. So we want to put these in order. This is, again, a handy tool. You draw your 1s, 2s all the way down, and then the 2p starts next to the 2s, and then the 3d starts next to the 3p and goes down, and the 4f starts next to the 4d and goes down. And then we draw these diagonal lines. So the 1s is the lowest energy, then the 2s, then the 2p, then the 3s. That's all a regular, you would think that would be the regular order of things. But then here's where it gets tricky. Then after the 3s, the 3p is the next order, the energy level, and then it's the 4s, not the 3d. So this captures the fact that the 4s has an energy that's lower than the 3d. and then you keep drawing. So you fill, or these orbitals are in this order of energy as you go up using this handy tool. And this is an easier tool to draw than this figure, this whole figure. Okay, good. So let's put these in order of increasing energy. So we're looking for the smallest one. We've got, typically you go for the smallest n value. So here's the 3D. It's right here. Are any of those others less than that? No. The 4D is right here. And so this is increasing in energy, so that's okay. So the 3D is the first one. 3D. And then what's next? We've got a 4P. Okay. And then the 4D. So 4P. 4P. Okay, so here we are at the 4P. It's tempting to go to 4D, but look, the 5S here is next. The 5S is between the 4P and the 4D. So we would do 5S and then the 4D. So we went 1, 2, 3 here, and 4 there. So this series of Alex problems is just kind of training you to use this tool here to learn the energies. Okay. This is another way to learn that tool, is to draw the little energy level diagram. And so Alex has some tool things where you can drag some boxes out of there and you can start filling things up. Now, this also trains the Hund's rule, where the electrons go into their independent boxes first. So spin up, like if it was, what element is this? Let's see if you can figure that out. Don't look at the text. It's too late. Don't think of a pink element. Right? So you look over here, you got hydrogen, helium, lithium, beryllium, and then 2 more in the P group, boron, carbon. You see here's the 2P subshell. We got 2 electrons. So carbon is what we call a P2 element. What is nitrogen? Nitrogen's a P3 element. Oxygen would be a P4 element. So we're filling up that P shell. But this outer shell, these are the valence electrons. So valence electrons. So it includes the 2s. 1s here, this would be a core electron. Okay. So have fun drawing those little pictures. And then trying to figure out the allowed quantum numbers for a particular orbital. So here we are, list all the possible values for the magnetic quantum number for a 3D electron. So M sub L is related to L. So it's equal to minus L plus 1. And we continue in that same trend, adding 1, 1, 1, all the way up to positive L. Okay, so we need to figure out what L is. It's a d orbital, so S, P, D, L equals 2. So this is going to be equal to minus 2, minus 1, 0, 1, and 2. Those are all possible values of the M sub L. So just practice learning the sets of quantum numbers. What's the principal quantum number for a 4f electron? So we're looking for n. N is that number right there. So n equals 4. Those are easy. If you're given an orbital, n is that number. Okay. What are the spin quantum numbers for a 4f electron? M sub s is always equal to plus 1/2 or minus 1/2. Those are the only 2 options. We designate those with an up arrow or a down arrow. So this one's pretty easy, but it's only easy if you know the relationships, right? If you don't know the quantum relationships, the quantum number relationships, then you're going to have to go to the explanation and burn a little bit more time. So let's see, how much more do we have? Yeah. 3 more problems. Let's see. Yeah, we'll start here next time, okay? This again is due Wednesday night, so we got some time. But take what you've done this morning in class and start on Wednesday, because there's a lot of problems. And if you start doing the explanations and missing things, it's going to take you a long time to do it.